Let's sketch the graph of the function f of x equals 3 times 2 to the x. So let's have a look at what the graph of an exponential function like this one, what that graph looks like, its general shape and form. Now, when you are graphing a function by hand for the first time, it's helpful to establish a table of values for the function, a table of xy pairs. So let's scatter a couple of x's in this table and let's calculate the associated y value so that we have some xy pairs that we can use for our graph. So let's try x equals minus 2, minus 1, 0, 1, 2, and 3. Now, because we are dealing with exponents, it may be easiest to start with the positive exponents, 1, 2, and 3. So that's what I'm going to do. Starting with x equals 1, let's plug this x equals 1 into the formula, and let's see what y value corresponds to that. So we have 3 times 2 to the power x equals 1. And let's simplify. Now we're following PEMDAS here, which means the first thing that we need to do is calculate 2 to the power 1. But anytime you have something to the power 1, then that something is just returned. So this is equal to 3 times 2, which is equal to 6. Let's try the same thing with the next point where x is equal to 2. We have 3 times 2 to the power 2. So, following PEMDAS once again, we have 2 to the power 2, which is 4, and then 3 times 4 is equal to 12. And once again, we can try it with 2 to the power 3. So this will be equal to 3 times 8, which is equal to 24. And this makes sense based on what we're seeing so far, because every time we increase the x value by 1 unit, the outputs get doubled, get multiplied by the base of 2. Okay. Now let's start working on the non-positive x's. Let's work on x equals 0. 3 times 2 to the power 0. Now 2 to the power 0 is equal to 1. Any number to the power 0 is equal to 1. So 3 times 1 is equal to 3, and this makes sense because we know that the y value corresponding to x equals 0 is what we have called the y-intercept. And the y-intercept is this number multiplied in front is the a value in our exponential function. Okay, now let's work on the negative x's, and this could be the hardest part. Here we have 3 times 2 to the power minus 1. Now when you have a negative exponent, the negative exponent causes the quantity to be reciprocated. So here, instead of 2 to the power minus 1, this is going to turn into the reciprocal 1/2. So this is equal to 3 times 1/2. This is equal to 3 divided by 2. And finally, for x equals minus 2, we have 3 times 2 to the power minus 2. So this is equal to the reciprocal of 2 squared. This is equal to 3 times 1/4. This is equal to 3 divided by 4. So a little review of negative exponents is useful. You probably learned them in Math 72, and then we have reviewed them here in Math 97. All right, now that we've got a collection of pairs of x's and y's, let's start sketching the graph of this function. So let's go over here on the side. I'm going to draw in the x-axis. I'm going to draw in the y-axis. I'm going to try and draw it so that it's rather tall. Okay, not quite square, a little bit top leaning, I would say. All right, So let's start, I suppose, once again, let's start with the non-negative x's. Let's graph these guys where x goes from 0 to 3. When x is 0, y is equal to 3. So I will go 1, 2, 3 units up, and I'll plot the point x equals 0, y equals 3. When x is 1, y is 6. So I'll go 1 unit in the x direction. I'll go 1, 2, 3 more units in the y direction, and I'll plot the point 1, 6. Now when x is equal to 2, y is equal to 12, which is already getting pretty far up there. I think it's just about out of range. So I'm going to try and graph that point, scroll up, graph it up here somewhere. Here is 2, 12. But I think that 3, 24 is going to be too extreme. It's going to be too tall. It'll be off the Word document. So that's not going to work. We'll just ignore that for now. Okay. So now we have the point where x is equal to -1 and y is equal to 3 over 2. So 3 over 2 is about 1.5. So I will graph a point at x equals -1 and y equals -1.5. And finally, we have the point where x is equal to -2 and y is equal to 3 over 4. So that's a little bit less than 1. That's 0.75. Okay. So now what I'm going to do is I'm going to connect these dots. So we have the graph connecting the dots on the right-hand side, which is quite steeply increasing. And then they're sort of leveling out like a plane is descending, almost as if a plane is descending onto the strip of road which is represented by the x-axis. Now here we've graphed this by hand. You're also welcome to graph it using Desmos.com or using your graphing calculator. But there are a couple of interesting things about this equation which I'd like to point out. In particular, there's one interesting thing that may not be very easy to see from the work that we have done so far, and that is that this graph never actually goes below the x-axis. It gets closer and closer to the x-axis as x becomes more and more negative, but it never actually becomes a negative y value. We never achieve that. So, interesting fact. The graph never crosses below the x-axis. The y values get closer to 0, but never become negative. And so, in general, exponential functions have this sort of swoopy shape, where on one side of the graph they're getting closer to the x-axis, and on the other half of the graph they are ascending very sharply toward positive infinity, toward the top, so to speak. Okay, let's try it again with another example. Here we have a base which is equal to a fraction. Sketch the graph of the function f of x equals 4, 1/2 to the power x. Okay, so here we have our table of values, x against f of x. And let's start as before, maybe with x is equal to 1. Now when x is equal to 1, I'm dealing with 4 times 1/2 to the power 1, which is equal to 4 times 1/2. So if you cut 4 in half, the result is 2. And when x is equal to 2, we get 4 1/2 squared. 4 times 1/4, which is equal to 1. Now when x is equal to 0, 1/2 to the power 0 is equal to 1, and I get the a value of 4. And this checks out so far. A equals 4 is showing up next to x equals 0. And every time x increases, our y values are being cut in half, multiplied by 1/2, which is our base. All right, now let's try it with x is equal to -1. And we have 4 times 1/2 to the power -1. So -1 is going to come in, and it's going to cause 1/2. So -1 is going to come in, and it's going to cause 1/2 to be reciprocated. And we get 8. Finally, for x equals -2, we take the reciprocal of 1/2 and we'll square it. 4 times 2 squared, and we get 4 times 4, which is equal to 16. And you can always go back and make sure that the general pattern that we expect to see checks out here. Every time our x increases, our y values are multiplied by 1/2, moving from 16 to 8, half from 8 to 4, half from 4 to 2, half from 2 to 1. All right, so let's use this information to put a graph together. Here is x, and here's f of x, the y-axis. And we found that when x is equal to +1, the y value was equal to 2, 1, 2. When x is equal to 2, the y value was equal to 1, 2, 1. When x was equal to 0, the y was equal to 4, 0, 4. And when x was equal to -1, y was equal to 8, 2, 3, 4. And then 16, once again, 16 is somewhere way up there. I'm not even sure if I could, let me just draw the dot up here, yonder. -2, 16. So let's connect the dots. And so here's our exponential function in the case that our a was equal to 4 and our base was equal to 1/2. Now notice that this graph has the same general shape as last time, but the graph is pointing in the opposite direction, I would say. It's flipped compared to the previous one. This one is going down as we move from left to right, whereas in the previous function, the function was moving up as we moved from the left to the right. And that's a consequence of having a base which is smaller than 1. Our y values are going down, are being cut in half as x goes up.